All right. Where do things stand? Review, recall. Up until that midterm, we were doing, we learned things like the product rule. I don't have to write it for you. Everybody knows it. The quotient rule. We learned the chain rule. We learned all kinds of the power rule, the log rule, the exponent rule. Once we had the chain rule, we learned about implicit differentiation, right? Chain rule allowed us to think about functions, differentiating a function implicitly as a function of another variable, implicit differentiation. I really am working on my handwriting. I don't know why this thing is getting worse and worse. And anything else? And related rates, right? Related rates was the last thing that we had covered, related rates. Implicit differentiation allowed us to do related rates because related rates are about our applications basically of implicit differentiation. We have one more topic in chapter 3. That's what we're doing today. And then we're moving on to chapter 4. I actually like this topic. I hope you guys will too. Our new topic, so this is the new topic is applications of calc. This is really very important, actually, very sort of immediately applicable, which is linearization. Linearization. Okay. So what do I mean by linearization? Let's do an example. Let's try to compute. So what is, bless you, the square root of 4.01? Well, you go get your calculator, right? You know what the square root of 4 is. What the square root of 4.01, the heck is that? You get a calculator and you ask the calculator. Okay. But before calculators, or even you'll see there are situations where we don't want to ask a calculator. How could you do this just with your mind? How could you get a decent approximation or a first order approximation? So what's a 0th order approximation? 0th, and I'll explain what I mean by order much later, not today. But the 0th order approximation is like the dumbest thing you could think of. The dumbest thing you can think of is, well, this thing is quite close to square root of 4, and I know the square root of 4, that's 2, right? So whatever this number is, whatever the square root of 4.01 is, it's going to be very close to 2. Any disagreements with that? That makes sense. How close? If I make a little change from 4 to 4.01, how much does that change to whatever the answer is of the square root of 4.01? That's what we can use calculus for. So let's think about this. Let's look at the function. Our function is obviously the square root of x. So we know what that function looks like. Here's that function, y equals square root of x. Okay, and we're interested in neighborhoods around 4. So near x equals 4, I want to know the value of this function, not at 4, but right here at 4.01. But first of all, I know the approximation, I know the value at 4, which is 2. Okay, so this is the point 4, 2. No surprises there. Now, is there some much easier function than the square root function that closely approximates the value of the square root function near this point? Can you imagine such a thing, Sid? The tangent line, the whole point of being a tangent line is it's very close to the function itself. The tangent line, let's call this y equals line L of x. L of x is the tangent line. The tangent line is a close approximation to the function itself in a small neighborhood. So if I go over here, the tangent line is not a very good approximation, right? But in a little window around the point 4, whatever the tangent line to this graph is, will be a decent approximation to the actual value. Does that make sense? And so let's work out what the tangent line is. So the idea, why don't you guys start working out what the tangent line is, and I'll just write this down. The idea is the tangent line to y equals square root of x at the point 4, 2 is a first order. It's like the next thing that you would think of. 0th order is just the value to, the first order is the next idea, is a first order approximation. First order. It's also called linear approximation. Linear approximation, because it's approximating the curve, this weird curve square root by a line. So that's what linearization is. Linear approximation, first order, or linear approximation. The tangent line to this is a first order or linear approximation to the curve, to f of x is square root of x, in a small neighborhood, in a neighborhood. And neighborhood doesn't have a technical definition right now. It's just nearby the value in a neighborhood of x equals 4. Okay, that's the idea. We're going to approximate the value. I don't know the value of the square root of 4.01, but I do know the value of L of 4.01. That's going to be very easy to work out. Much easier than working out the square root. And I think that one will be an approximation for the other. Okay, does that make sense? Okay, does anybody have the tangent line yet? What is L of x? Okay, you're saying it's 1/4 x plus 1. Let's see if I agree. That sounds very plausible. So the derivative of square root is 1/2 x to the minus a half. I'm interested in that when x is 4. So I evaluate this at x equals 4. Evaluate this at x equals 4. That's 1/2 x to the minus a half is a x to the 1/2 in the denominator. X to the 1/2 is 4 to the 1/2, which is 2. So I do get a slope of a quarter. That agrees with that. And then the equation I'm thinking of is y minus 2 is equal to a quarter x minus 4. And indeed, so if I move the 2 to the other side, the 1/4, so this is a quarter x, bless you, a quarter x minus 1. And if I add 2 to both sides, I get a quarter x plus 1. And that is indeed the equation of the, good job, Dan. Did everybody get that? This is something that we're really good at by now, right? Just computing the tangent line to a curve at a point. This is our bread and butter. Great. That's the linear approximation. Well, so what is the value of this? So the first order approximation, so approximate f of 4.01 by L of 4.01. And what is L of 4.01? So L of 4.01 is very easy to work out. What's a quarter of 4.01? A quarter of 4 is 1. A quarter of 100th is 0.01, 0.0025. Because if I multiply this by 4, 25 times 4 is 100. That'll get me a 1 right there. And then there's a plus 1. So I think the answer is 2.0025. I think that the square root of 4.01 is not just 2, but it's going to be, I think, close to 2.0025. Everybody see how we got that? All right. So let's check. What is the square root of 4.01? How about that? 2.002498. Not bad. The real value, the real answer, square root of 4.01, and in other words, the actual f value is 2.002498. 002498, and we, without doing any work, got 2.0025. What do you think? Not bad? All right, you get the idea? Let's do a whole bunch of these. Let's do one more before we talk about what's going on in general. Let's approximate the square root of 3. Any questions on this one? You see what we did? Okay. Example. What is the square root of 3? Here it's not so obvious what you're supposed to do. Square root of 4.01 very obviously begged you to look at 4, the square root of 4, which we know. What are we supposed to do with the square root of 3? Any ideas? No ideas at all? What's 3 next to? It is next to e, but I don't know the square root of e any better than I know the square root of 3. 4. Oh, 1. It's also next to 1, but it's much farther from 1 than it is from 4. We can again use the square root of 4 as our sort of guide. Now, why? Why is that going to be decent? Because the square root of 3 is the square root of 4 minus 1. And let me pull out a square root of 4 from the radical. So if I pull out a square root of 4 from the radical, what comes out? 2, right? 2 times 1 minus a quarter. So this is a small perturbation. A quarter is my neighborhood. A quarter is a small number, relatively speaking. It's not as small as 1/100th. This is just 1/4, but it's a relatively small number. And so we'd like to understand. So let's take our function f of x to be what? 2 times the square root of x? 2 times the square root of x. And we want to know the value near x equals 1. X equals 1 is the value that we know. The value that we really want is near 1, namely at 3/4, at 1 minus a quarter. Does that make sense? Do so. Where did I get a quarter from? So if I pull out a factor of 4 from here and from here, then that 4 turns into a 2 in front. And what's left is, so if you multiply this out, this is 3/4. And if I multiply the 2, that's 3/4 times 4 is back to the 3 that I had there. Okay, does that make sense? Okay. So you want to take a minute and do this calculation? Go take a minute and see what you can work out. So now we're looking at 2 root x. This is 2 root x near x equals 1. Okay. That's the point 1 comma, I guess, 2. And the tangent line is going to be something. And I'm interested in the value at 3/4. So I'll take this approximation to this true value. So what are we doing? Everybody's hard at work. I see a lot of pencils moving, so maybe I should just leave you alone. You got it already, Robin? You got to use it? No? You're thinking? What do you think? What are you thinking? What's the first thing we should probably do? Yeah, what's the derivative of this? Yeah, 2 times a half x to the minus a half. I agree with you completely. That's 1 over root x. Okay, we're going to look at this at x equals 1 or near x equals 1. So the slope here is 1. Okay, so I didn't draw it very well. The slope should be 45-degree angle. Okay, so the value, the linear approximation is that the value is 1, the derivative is 1, and we have x minus 1. It's kind of 1s everywhere. Did anybody get this for the linear approximation? Yeah. Okay. And so if I plug in 3/4 for this, so if I look at L of 3/4, 3/4 being this value, 3/4, L of 3/4 is 1 plus negative a quarter. Did I get that right? something I don't like about this. Oh, the value of the function is not 1, but 2. The value of the function is 2. This is 2 plus -1/4. Something I didn't like about that. Okay, so $2 minus $1/4 is $1.75. Is that what you guys got? Did anybody get this approximation? And the true value of square root of 3, 1.732. Okay, square root of 3 in actuality is 1.732. It's not nearly as good as the approximation we had before, but the value where we're taking the approximation is quite a bit further away. This is 1/4 as opposed to 1/100, so you can't expect to do that much better. But pretty close without doing any work. Does that make sense? Yusuf, now does it make sense what we were doing? Okay. So what's going on in general? What's the general process? General procedure. If we have a function, so we have a function, we have a graph, y equals f of x. Let's think about the graph. Y equals f of x. Okay, and we have some point A where we want to approximate. So the linear approximation to f of x near x equals a is the line, which is what? So if this is the point A comma f of a, the slope is yeah, f prime of a, exactly, the derivative. Okay, so the value, so the equation of this line is f of a plus the slope f prime of a times x minus a, right? This is the same thing as slope intercept, not slope intercept. What is it? Point slope form, right? We would write y minus f of a is equal to slope f prime of a times x minus a. And all I'm doing is moving this f of a over here. So this is the linear approximation. And if you look back, this is exactly what we did in both cases. Does that make sense? Now, by the way, there's quite a bit of choice when you're doing things like computing square root of 3. If you look really a little further back, we can use the same linearization. Let's look at this linearization. If we're thinking about the square root function, if we plug in 3 for x, this is the value in a neighborhood of x equals 4. If we plug in 3 for x, we get the same 1 plus 3/4. We get the same 1.75. Even though we chose a different function here to use our approximation. It's the same, it's still square root. It's still a square root function at 4. Here we called it twice the square root function at 1, which is the same function, just slightly, reformulated. So this is a general procedure which will allow you, in whatever context you like, to give an approximation to a function, to a known value of a function, using just its derivative and how much you're fluctuating from. But let's do another example. We'll get better and better at this. All right, why don't we make this the quiz? I think this is a good one. Let's do a little quiz. Let's approximate. Approximate, in other words, linear. Give me, what's the linear approximation? Linear approximation. What is the linear approximation of cube root of 7? Okay. So why don't you take 5 minutes and let's see if we can work out the linear approximation to the cube root of 7. And let me know if you need a hint. I'll come around. function? Well, what function? First thing I would write is f of x is cube root. Cube root of x that we want. All you need is derivative. And what cube root? You want to use that one. That's the thing. Cube root. We'd like to have a as your value of the cube root. Yes. No. Any value nearby a known cube. What are the cubes? What are the cubes? Well, the value of the function is at 8 the cube root of 8. That's the cube root of 8. So we try to set A equal to T. That's like our angle. How many are done? Can I see a thumbs up? Okay, just a couple of you. How many are still working? Okay, great, great. Keep going. Keep going. So yeah, what is your thing? What about the derivative? No, it's time is the break. Well, you already have it. Third. I mean, are you still working? Okay, keep going, keep going. Yeah. That's right. Yeah, exactly. So there you go. Linearization. So the approximation of that function is f of a. Yeah. I think you got it. You almost got it. How many think they have it now? Okay, still not too many. Should we work on it together? All right. Let's see how we did. So what function did you guys think of to try to solve this? The cube root function. That's the only thing that's floating around. So f of x is cube root of x. The cube root is x to the 1/3. right? What's our anchor point? What's the point A where we're going to want to apply the approximation? It's got to be something where we can easily evaluate the cube root. 8. 8 is a cube root that we know. So our anchor is 8. I like to think of A as anchor. Like, where are we going to hold on to? Where can we evaluate things? All right. F of A is f of 8. The whole point is the cube root of 8. This is 8 to the 1/3. Cube root of 8 is 2. Beautiful. All right. We're going to need the derivative. The derivative is x to the 1/3. That's 1/3 x to the minus 2/3. So what is the value of the derivative? What's our slope at a being 8? So I have 1/3, and then x to the minus 2/3 is an x to the 2/3 in the denominator. That's 8 to the 2/3. Oh my goodness, 8 to the 2/3. It's a good thing we reviewed our pre-calculus in the first couple of weeks. I told you it'd keep coming back. Okay, but 8 to the 2/3 is 8 to the 1/3 squared. 8 to the 1/3, we already know, is 2. 2 squared is 4. Or if you square 8 first, you get 64, and then the cube root of 64 is 4. 4 times 4 is 16. 16 times 4 is 64. So there's a variety of ways you could have done this to see this is 1/3 times 4, and 3 times 4 is 12. Okay, so the linear approximation to this function near x equals 8 is f of a, that's 2, plus f prime of a, that's 1/12, times x minus a, whatever x is, and a is our anchor point, 8. So that's a linear approximation to, this is linear approximation. This is the linear approximation to f of x equals x to the 1/3 near x equals 8. We will evaluate it at x equals not 8, but 7. That's what we want. At x equals 7, then the cube root of 7 is roughly equal to, so it's quite a big move from 8 to 7, but actually you'll see it's not that bad an approximation. 2 plus a 12th times 7 minus 8. 7 minus 8 is -1. 2 minus a 12th. 2 is 24/12. Minus 1/12 is 23/12. Is that what you guys got? Okay, so if you thought to use the cube root function, give yourself a point. If you thought to anchor it at 8, give yourself a point. If you evaluated f of 8 and realized the cube root of 8 is 2, give yourself a point. If you computed the derivative correctly, give yourself a point. If you evaluated the derivative at the anchor point correctly and got 1/12, give yourself a point. If you wrote the linear function, it's a lot of points here. Give yourself another point. And then if you plugged in x equals 7, give yourself another point. So however many that is, 7 points or whatever. How many got a full score on this? Yes. Yes. Okay, pass them on down. Peter, if you wouldn't mind collecting them, please. Very good. You guys are getting the hang of this, right? Makes sense? What is 23/12? 1/12. I'll just do it on the computer. 23/12. 23/12 is 1.916. So our approximation, 23/12 is 1.9166. And what about the cube root of 7? Cube root of 7, 1.9129. Cube root of 7 in actuality is 1.9129. Not too shabby, would you say? Okay. All right. Very good. Let's introduce a little bit of terminology. So again, we have this, where was it? This formula. Can I grab it? Move. Zoom is in the way. Go away. Can I grab this formula? Bless you. Copy. Let's go over here. Paste. Okay. So this was our linear approximation formula. Now let's think about what's really going on here. If we're going to use this as a linear approximation, what's really going on? Going on at another level. Here's again our function f. Okay, this is f of x. Y equals f of x. Here's our point A. Here's our linear approximation. This is y equals L of x. Okay, the true height here is f of a. The change, we're changing from A rather, to x. So that's a little change in x. That's a differential in x. That's a little change in x, which we can write as dx. This is a little change in x. A little change in x. And the value of L at this point x is the value of f with a little change. So what is this? What is this height? Let me move this out of the way. What is this height? This is f of a. This is L of x. Okay, so the difference between L of x and f of a is this stuff. This f prime of a, x minus a. That's how much the y is changing. That's dy. That's a differential in y. Differential in y. In other words, when I wiggle x by a little bit, how much does the output change by? That's what this differential, that's this bit of the linear approximation is called the differential. How much do things change by? In other words, we know the cube root of 8. The cube root of 8 is 2. When I move from 8 to 7, how much do things change by? Or when I move from 8 to anything, how much do things change by? So here's our linear approximation function. Let me grab this. So, for example, near if f of x is equal to cube root x, near x equals 8. In other words, that's what I'm setting my anchor point to be, 8. This is how much you need to change from the cube root of 8 being 2 to your cube root of whatever. If you want 7 or 7.5 or 9, if you want to compute the cube root of 9, this is how much things will change by if you replace 8 by 9, right? This is the change from the known value of 2. 2 is sort of what we know. We know the cube root of 8. And if you want to change to something like the cube root of 7 or cube root of 9, that's going to change 2. How much is it going to change? This is the differential. This is the change in the value. Does that make sense? So people get very confused when they see things like this. Let's look at what we're really writing. What we're saying is that the differential, so y dy, let me write something and I'll try to justify it. Dy is f prime of x dx. Okay, so you're used to seeing dy dx. If I said dy dx is f prime of x, you wouldn't have any problem with this equation because this is what we've been doing all along. This means an infinitesimal dy, an infinitesimal change in the numerator, and an infinitesimal change in the denominator. And in the limit, we get the derivative, right? But now I want you to change what you think about this. So this used to mean, let me write this down. This used to mean infinitesimal, infinitely small, infinitesimal, I think I got it right. Infinitesimal change in x gives rise to an infinitesimal change in y, decimal change in y, and in the limit that measures the derivative. right? Which in the limit is the derivative, which in the limit measures the derivative. And what we're doing now is saying, well, don't take the limit. Now, don't take the limit. When you want to understand linear approximation, don't take limits. Don't take the limit as dx goes to 0. Just leave dx. Just leave dx to be whatever it is, a finite, hopefully small-ish, small, whatever that means, value. And then you'll get a finite small value for dy. And we'll get a small finite value for the change in y. Does that make sense? So if you think in terms of symbols, I mean, these symbols had a meaning. The meaning of these symbols was this is supposed to be like 0 over 0, right? This indeterminate 0 over 0 where we differentiate. And it's useful to reinterpret these symbols as meaning an actual change in x and an actual change in y, and that ratio being approximated by the derivative. Okay, so the derivative is so the differential in y. So this has a name. This is called the differential. I prefer, somebody asked me about this, maybe Rohan, somebody, I can't remember, a long time ago asked about differential in y. I would write this as differential in y, just so as not to confuse the notation, because I think people find this confusing. I would say a differential in y, f prime of x, is equal to the slope times the differential in x. But your book and many other people just use the same symbol when they mean a finite value versus when they mean an infinitesimal value whose limit we should be thinking about. Okay, so don't get confused about those two things. Is the distinction making some sense? Is this clear? Let's do another example. Let's do an example. What is the differential of y equals cosine of x? Okay, what's the answer? dy is negative sine x dx. So it's almost like you're implicitly differentiating with respect to an auxiliary variable, dt, except you're not putting the dt's on the bottom. If this was implicit differentiation, if x is a function of t and y is a function of t, and y, I'm writing y, but really y is a function of t, then you would say dy dt is equal to, now I would implicitly differentiate this, negative sine x dx dt. Right? That is now familiar to us when we do implicit differentiation. And now all I'm saying is forget about the dt's on the bottom. Just leave it dy is equal to negative sine x dx. And this is a useful concept because once you see it like this, you can easily do things like approximate. So here's another or continuation of the example. Approximate cosine of 2 pi. Let's make it pi over 2 minus 0.1. Okay, so if your function is cosine, y is cosine of x. What's the differential? How much am I moving x from the value, from a known value? Negative 0.01, negative 0.1, right? So again, let's think about the picture. Here's the cosine function, y equals cosine of x. Okay, pi over 2 is over here. I know the value of cosine at pi over 2. is 0. So cosine of pi over 2 is equal to 0. So this is pi over 2. And the question is, if I evaluate it just a little bit before pi over 2, so this is my dx, it's a slightly negative change from a known value. The differential, so dy, how much y will change, is negative sine of x times dx. And dx is negative 0.1. Negative sine of x when x is equal to pi over 2, this is at x equals pi over 2. What's sine of pi over 2? Sine starts at 0, goes up to 1, then comes back down. So sine is 1. So this slope is negative 1 because it's negative sine. This is 45 degrees down. So this is negative 1 times negative 0.1. And so the negatives cancel and I get 0.1. So I know right away how much I need to wiggle. If I wiggle x to unknown value, I know how much I need to wiggle the result from being a result of 0 to a result of something near 0.1. Does that make sense? So the differential tells you how much things change by. So let's write that down. Differential dy tells you how much y changes by how much y changes, tells you by how much y changes when x changes by dx. Okay, does that make sense? We need more examples. Okay, we do a bunch of examples, then we talk about general theory. Let's do more examples. All right, let's compute a couple more differentials. I mean, computing differentials is no different from computing derivatives. You just write the symbols slightly differently. Here's a differential. What is the differential of tan x? Secant squared x dx times dx. Pretty simple, right? Let's do an application. I think you'll see how this is useful in application. So here's an example. Application. I think I have a good one here. Yeah, okay. You're going to measure, you have a deep well, okay? There's a deep well, and we're going to measure its depth by dropping a stone. We're going to take a heavy stone and just roll it off and drop that stone. It will time from when we drop it until it hits the bottom. We'll hear the splash, right? Dropping stone and waiting for the splash, when it hits the water down here, okay? And that will tell us how far it fell. Why? What's the equation of motion of a stone, of a falling body? What's the initial position? 0. Initial position, let's say, is 0. So we're measuring negative height. Initial velocity, 0. We're not pushing it down. We're just letting it go. And then the let's say we're measuring in feet. So the in gravity, the acceleration due to gravity, 32 feet per second squared. Times t squared over 2. Right? That would be the equation of motion of this thing. So let's say we can measure the time, but we're going to start a clock when it starts falling. We're going to wait for it to fall, and then we'll stop the clock. And we're not perfect. Nobody perfectly, the sound. First of all, the sound has to travel, but never mind. Let's pretend that the sound instantaneously hits our ears the instant the stone hits the water. Sound travels very quickly, but not quite as quickly as light, and nothing travels instantaneously. But again, never mind all of these things. The instant it hits your ear, the sound of the splash, your brain has to process that sound and send a signal to your thumb to push the button to stop the stopwatch. And that takes 1/10 of a second or something. Okay, so we think that we can time the stopwatch. We have a error estimate for the stopwatch of, let's say, give or take 0.1 seconds. Okay, that's how accurate we think our thumb is in stopping the clock. Given that error, what is the error in the measurement of the depth? So what? You can see my cursor is moving, right? It's just not writing exactly. That makes it even harder to write well. Okay, what is the estimate of the expected error, the error in measuring the depth? In measuring depth. Okay, does this make sense? Does this seem like a reasonable thing? You know, if you have a deep well, you don't have a stick that'll reach that far down. You for whatever reason want to know how far down it is. So, oh, I got a great idea. I know the equation of motion. So I just put the stone in, hit a stop clock. The second I do it, I got a buddy of mine to hit the stop clock while I'm throwing it in. Okay. Once I hear the splash, that's exactly the value of t. That's the equation of motion. So let's simplify this. 32 over 2 is 16. So I get negative 16 t squared, right? If it falls for 2 seconds, then the depth is t squared. If it falls for 2 seconds, then t squared is 4. 16 times 4, 64, right? Then it's 64 feet down. If we waited 5 seconds, 25 times 16 is 100 times 4, 400. Then it's 400 feet down, right? We can tell whether it's 64 feet down or 400 feet down based on if it took 2 seconds or 500 seconds. But how much of an error will we accrue due to the fact that our finger isn't perfectly connected to our ear? So if we have this much of an error in t, in the measurement of t, how much error will we have in the measurement in s? That's exactly the differential. Okay, so what is the differential? The differential of s. So if s is equal to negative 16 t squared, the differential of s is negative 32 times t times dt. So if dt is give or take 0.1 seconds, so ds is negative 32t times 0.1 seconds, 0.1. In other words, ds is negative 3.2 t. So if we measured that it fell for 2 seconds, then the depth s, what did we say, was 64 feet? Is that a question, Roger? Yeah, please. You want to say plus or minus here? Yeah, well, I was saying that I don't know that it's a positive dt, right? So it's a plus or minus of 0.01. So this is really a minus plus. If I'm early, if I anticipate it, then let's say that I can't possibly anticipate it. I know I'm going to be late. Let's make it a positive plus, positive 0.1. Okay, an error of as much as positive 0.1. So if I'm late by 0.1 seconds, just not to confuse things, but yes, if you don't know which way your error is going to go, then it would be a plus or minus. So if I'm late by 0.1 seconds to the clock, if my time is extended by 0.1 seconds from the true time, then my error estimate is minus 3.2 t. So if t was 2, if the measurement should have been 2, but I measured 2.01, well, how should I put this? If I measure 2.01, then if I measure 2, then my error estimate is 64 feet. Then my depth estimate, my depth calculation is 64 feet. But the change in that depth is negative 6.4. Okay, so I should probably take, because I'm just setting t equal to 2 in this, I should probably take 6 feet off of my estimate for the depth, because that's how much I'm expecting to be off. Does that make sense? If I measure exactly 2 seconds on my stopwatch, but I think I'm 0.1 second late to hit the stopwatch, I don't just say, well, I measured 2 seconds, so it's 64 feet. I would say, wait a second, I'm probably over by 6 feet. It's probably more like 58 feet. Does that make sense? As opposed to if it fell for 5 seconds, if the time was 5 seconds, oh, I'm using S for seconds and S for position. Let me drop the units so that I can't drop position, but I can drop the units. Then I expect the depth of the well to be, what did we say? 400 feet. 400 feet, but I'm probably overestimating that, because if t is 5 times negative 3.2, negative 16, I should probably take 16 feet off of my estimate for the depth. It's really probably more like 384 feet. So true depth is likely, or a first order estimate to the depth is 384 feet, not 400. Does that make sense? So this differential is exactly what it tells you. Now, the longer the time, the longer the stone falls, the more you have to adjust your expected error. The larger your expected error in absolute value. Does that make sense? Okay, should we do another one of these? Get some more practice with them? You guys look confused. I realize this topic is slightly confusing. It's applications. It's like related rates, right? Once we have a real life example, you guys like the abstract somehow. As long as there's X's and Y's, you're perfectly happy. Once there's boulders falling in free fall, then it gets scared. What's that? This is way more interesting? Okay, good. Good. I'm glad you think so. But the looks I'm getting are much more confused. Now, how many are following what we're doing? Okay, awesome. How many are bored? Am I going too slow? Making too big a deal? Okay, a couple of you are bored. Please be honest. I need to know if I should go faster. You guys are too chicken. Tell me if you're bored. All right. Let's do another example. You want to approximate, you're gonna like sweep out a big field, and you're gonna sweep it out by just walking diameter. So there's a big circular field, and you're gonna plant corn or whatever. You need to know its area. But you're not going to measure the area. You're just going to, walk the length of the diameter. Walk the length of the diameter. Sorry. Is it? Oh, okay. We have a big circular field. We need to know its area. We'll walk the length of the diameter and estimate from there. Okay, here's a big circular field. We're going to walk the length of the diameter. So if this diameter is, I can't use D because I'm going to want to use differentials. L for length. L is linear approximation. You're going to walk the radius. R. What is it? 2R, perfect. You're going to walk the length of the diameter, which is 2R. Okay, so that's how much you're going to walk. But you want to figure out the area as a result of that calculation. The area is pi r squared. Okay, pi r squared. So as you make an error in the measurement of R, how much error will you make in the measurement of the area? Let's say your shoes, you're measuring a foot with your shoes, but your shoes aren't exactly a foot. They're like 13 inches instead of 12 inches, right? Shoes are 13 inches, not 12 inches, which would be 1 foot. Okay. So does everybody understand the scenario? Okay. So how would we measure what our differential? So what's the differential in area? 2 pi r dr. Okay. Dr is 1 inch. Dr is 1 inch. Dr is 1 inch because we're off from the correct measurement by an inch. We're overshooting the correct estimate by 1 inch. So that's it. So 2 pi is like 6. So the change in area is about 6 times r, and dr is 1. So depending on how big your field is, maybe you have a field that's 10 feet across. If it's 10 feet in radius, 20 feet across. Okay, so if the radius is 10 feet, then you're saying that the field has an area. You would say that the field has an area of pi times 100, right? 314. This is like 314. But the true area, because you're dr is you're overshooting. So you're measuring 13 inches, but you should be measuring 12. So dr is -1 inch. -1 inch. Okay. So the change in area, because the radius needs to change by -1 inch every time you take a step, the change in the area should be -6 times whatever the radius is. So dA this is a general setting. In the setting of 10 steps, dA is -60. -60 square inches. Okay, square inches. Inches squared. So you should take 60 off of that 314 from the fact that your shoes aren't exactly 1 foot. Does that make sense? Whereas if it was 20 feet, in radius, 20 feet in radius, 40 feet across, then you would say the area is 400 pi. 400 pi, if pi is 3, can I take this number and multiply it by 4? 12 to 6, not 2, 5, roughly. I'm just multiplying this 314 by 4. Okay, but the change in area would also be -6 times r. -6 times r is 20. And so that gives me -120. So I should take 120 off of this to get a more accurate estimate of the area. So more accurate. This is the 0th order estimate of the area, just based on the fact that I took 20 steps, but a more accurate estimate of area. Is 1136 square inches. If I take 120 off of 1256. Does that make sense? How many are following? Okay, great. Good. Let's do a couple more examples. Yeah, so it's clear what I mean by the differential. So we already took a quiz, so I'm not going to ask you for this. But what's the differential of x to the 5th plus 7x, if that's your function? All together now. 5x to the 4th plus 7 dx. Who said? Julius. I'm still seeing, as I grade the midterms, I'm still seeing people write stuff like this. What's wrong with this other than Julius? The parentheses. It's not 7 dx. It's 5x plus 4 plus 7 dx. Okay, make sure you're not making mistakes like this. All right. You make up a scenario. Let's do another example. Make up a scenario. What's something where you would have an error in your estimate and you would need to adjust the estimate knowing that you're going to make some kind of error? What is it? Getting up in the morning with no alarm. Go on. When you hit the alarm. Okay, and what's the function that we're measuring? The time at which you get up? And what's the function between how much time there is? Wait, there's something here. Let's work with this. What's the rule in improv? You never say no, you say yes and continue. So you hit the alarm clock. So you wake up, you're supposed to wake up at 8 a.m. And get out of bed. But you hit the snooze. You hit snooze. And the amount of time that you sleep extra, there's a quadratic relationship or something. Let's say time out of bed, because once you're awake, you still might lie there for a minute, like on your phone or something, before you actually get out of bed. Okay, so time out of bed once awake, is a function of time, which is t squared. I don't know why t squared, it just is. All right, you see, it's not so trivial to make up these problems. You see what I suffer through when I make an exam. Time out of bed once awake is t squared. Okay, so what's the differential? So df, the differential of this function, will be 2t dt. So if there's a differential between now when you hit snooze, let's say you hit snooze at 8, I mean, you hit snooze a bunch of times, but you hit snooze at 8:20, right? You hit snooze at 8:20, but it's not exactly 8:20 that you know, it takes your hand a second to reach over and hit the snooze button. So the dt is 10 seconds. 10 seconds from still going 9, 10, now snooze. 3 seconds. I like 3 seconds. So 3 seconds is you know, it's 10:20. You do want to be awake and still lying in your bed for the next 20 minutes. So that's 20 squared is 400 minutes until you're at bed. I really hope not. But the dt is 3 seconds. Okay. Oh, this is seconds. This is measured in seconds. That's better. T is measured in seconds. Whatever. Okay, we're making this up. Time out of bed, expected time out of bed will be, well, the 0th order approximation is that it's been 20 minutes. We're measuring in minutes or seconds. We have to choose one. Yeah, actually, let's continue measuring in minutes, but then that 3 seconds is 1/20th of a minute. 1/20th of a minute. Let's continue measuring in minutes. Okay, so this is in minutes. So it's been 20 minutes squared. So time out of bed is 400. The units are all screwed up. It's 400 minutes. I don't know why it's minutes squared. That doesn't make any sense, but whatever. The expected time out of bed is 400 minutes after 8 a.m. Because you hit the snooze button at 8:20, and that's 20, and 20 squared is 400. Everybody see what we're doing? Okay. But we have to adjust the fact that if you think you're hitting it at 8:20, you're actually not going to hit it at 8:20. You're going to hit it at 8:20 and 1/20 seconds. So the adjustment, the differential, let's use the terminology, the differential between this naive expectation and the true expectation. Is this tomorrow? 800 minutes. How many hours is that? You're not getting out of bed today. Just try again tomorrow. The differential, God, the differential is 2 times time of 20 minutes with a 1/20th. Oh, that worked out. Actually, that randomly worked out. Usually I have to then massage the numbers so that they're not too awful. All right, 2 times 1/20th. You should be off by 2 minutes. Okay, so you'll actually get out of bed 2 minutes later than this predicts you will. All right. Does that make sense? I didn't think it would be that hard to come up with other scenarios of this nature.